What is alt multivariate, gang? Today we are going to be learning about rectangular coordinates in 3 space. This is the third take of this video. The first one was too long and the second one I had my mic off, so let's try and do this right. This is your first ever multivariate calculus lecture video by me, Daniel Weber. Yay! So let's get it started. Alright, first we got to talk about the 3D coordinate system. Everything you guys have done so far has been in a 2D coordinate system. The X, Y coordinate system. There's a common coordinate system out there. Easily, probably the most useful coordinate system out there. That's been good stuff. And you've been dealing with graphs, for the most part, where Y is a function of X. And that's all good stuff. But for multivariate, we are going to have to introduce you to a third coordinate, the Z coordinate. All right. So what are some properties of the Z-axis? All right. So in the same way that the X-axis is perpendicular to the Y-axis, the Z-axis is perpendicular to the Y-axis. The Z-axis is also perpendicular to the X-axis. It's perpendicular to both of them. It is the axis which is perpendicular to both the X and Y axis. That is its definition. So why does the Z point this way and not this way? Well, it could point either way, but we choose to go ahead and make it point up for reasons we will talk about it later. Because it points up, that makes our coordinate system a right hand coordinate system. That is a coordinate system in which we can use the right hand rule, which we will talk about later when we talk about vectors. We will ignore that for now. All right. So this coordinate system, this 3D coordinate system, has a couple names that you got to know. It's the Cartesian coordinate system. Named for none other than René Descartes. I think is how. It's something like that. All right, René Descartes, that's the I think, therefore I am guy. Didn't think of him as a mathematician. Neither did I. I'm not entirely sure why he came up with this thing. But he did. This is the Cartesian coordinate system. It is also called the rectangular coordinate system. And this is actually kind of important. Pay attention here. Because the reason it's called the rectangular coordinate system is because of how you can define a point in this coordinate system. All right. Let's say you've got this point right over here. You want to know where this point is relative to our origin, which is right here. Well, you can think of this point as being the corner across from the origin of the rectangular prism with y length with x width and with z height. This length is different. There we go. That is, its coordinates are rectangular. They are all at 90 degrees to each other, and any two points can define opposite corners of a rectangular prism. That's what makes it rectangular. And we're going to talk about some other types of coordinate systems. So take note. Rectangular. All right. Quick side note. This is not super important. But just in the same way that our 2D coordinate system has 4 coordinates. Nope. 4 quadrants. 1, 2, 3, 4. Our 3D coordinate system has 8 octants. 1, 2, 3, 4, 5, 6, 7, and then there's one in the back there. 8. All right, that's not important. I've never been asked to identify what octant a point is in, so that's not a big thing. Just something to be aware of, something to keep in mind. All right. Next, we want to talk about distance in 3 space. What's the distance of this little diagonal right here from corner to corner? We want to know how we can find the distance between any 2 points in 3 space. All right. So we've got this point here, and this point here. We've got this point, which is x. Yeah, we're going to call it x1. Yeah. No. We're going to call that one x2. x2, y2, z2. I changed my mind. This is going to be point number 2. This is going to be point number 1. x1, y1, z1. Okay. And for the sake of simplicity, just for right now, we are going to put point number 1 on the origin. Okay, and that's just for simplicity's sake. So we can ignore these for now because they're all 0 because we're on the origin. Boop. Okay. And we don't really need these 2's right here, because it's the only one. We don't need those point numbers, so that's just on the origin. Let's just make this a little bit simpler for us. Okay. So how do we find this distance right here? This distance, D. What we got to do is we got to take this segment D, and we got to split it up into its components. Its components along these axes. We have to find we have to find this distance in terms of this x, y, and z. So how do we do that? All right. So first, we split it up into a triangle. Now, what do I mean split up into a triangle? So we know that this line segment, no matter what line segment it is the hypotenuse of some right triangle that we can draw. And we're going to go ahead and draw that triangle. Boom. Right triangle. We have this red line, which is z units tall, between our second point and the xy plane. And we have this line, R, running from our point, the origin, to where this line Z intersects the xy plane. And we know that that this line is perpendicular to this plane and therefore perpendicular to this line. Because that's just, we're defining it to be that way. We're defining this to be parallel with the z-axis. So if all of those things are true, then we know that d squared equals r squared plus z squared. By the Pythagorean theorem, that must be true. All right, but what else do we know? What else do we know about this little thing r? Well, that same thing that we did with D, where we made it the hypotenuse of a right triangle, that's what we are going to do with R. Let's do that. So, we're going to split up into this leg and this leg. This triangle with hypotenuse R is going to have legs. Well, this leg is just its x component, right? Right. And this leg is its y component. And if you don't believe me, this is really the y component. But this length and this length are the same because all these are right angles. Because x, y, and z are all at right angles to each other. And it forms a rectangle, and we know that this has to be congruent to this if it's a rectangle. Just if you're having trouble with that. All right. So by this, we know that r squared equals x squared plus y squared. Right? Pythagorean theorem. Right triangle. R is the hypotenuse, x and y are the legs. But what that means is that d squared equals x squared plus y squared plus z squared. Right? We're just plugging x squared plus y squared in for r squared in this thing. And we get this thing. So we get that the distance equals the square root of x squared plus y squared plus z squared. Okay, now, that's when we made the problem simpler for us. We're going to go ahead and move this thing just a little bit. I'm going to move it to some point here. I think that's about where we had it before I just simplify. All right. And instead of going from 0, 0, 0 to x, y, z, we are going from x1, x2, nope, x1, y1, z1. Here, let me draw it somewhere where you can see it. x1, y1, z1 to x2, y2, z2. And what does that mean? How does that change all of our stuff? It doesn't change our stuff very much. All that means is that this z distance right here is instead z1 minus, or z2 minus z1. That this y distance down here is instead y2 minus y1. And that x distance over there is x2 minus x1. No big deal. So we get that our distance formula for any point, in any 2 points in 3 space, is d equals the square root of x2 minus x1 squared plus y2 plus, nope, minus y1 squared plus, I have to move this d now, z2 minus z1 squared. Make that a little bit longer. Go ahead and make this all, I don't know, let's make it orange just so you guys can see it. All right. D equals the square root x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. And you'll notice that this looks just like our distance formula in 2 space, which is d equals x2 minus x1 squared plus y2 minus y1 squared. Same, except for this little z term. Add the z term. It really is that simple. Just add the z term. Okay, let's do a practice problem. Example number 1. Find the distance between the points 3, 2, 8 and the point 1, negative 1, 2. Okay. So, all we do is we just plug it into our formula. We know that d equals the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. We got to pick a point 1 and 2. I'm going to go ahead and call this one 0.2 and this one 0.1. All right. So we get the square root just for reference of 3 minus 1 squared plus 2 minus negative 1, so plus, here, let's do minus negative 1 squared plus 8 minus 2 squared, which gives 2 squared plus 3 squared plus 6 squared, which gives the square root of 4 plus 9 plus 36, which gives us the square root of 49, which is 7 units between 0.1 and 0.2. All right, that's all on the agenda for this video. Hope you guys are rocking it. Keep on math.